Good evening, everyone. It is my great pleasure to welcome you tonight to the campus lecture of our distinguished alumni, Dr. Marc Stoecklin. He's head of security research at IBM Research Europe, and he comes from Zurich today. We're delighted to welcome him back to campus to celebrate his achievement as he received last year the EPFL Alumni Award, which is an outstanding contribution for his outstanding contribution to science, technology, and society. On behalf of the EPFL community, I would like to express our deep pride and warm congratulations, as Marc's career is a wonderful example of how research within industry can lead to groundbreaking innovation and real-world impact. His talk is very timely, as you know, as we have this year the International Year of Quantum Science and Technology, and the topic he will address tonight lies at the heart of it. But before, I would like to welcome Dr. Jean-Pierre Hubaux, Academic Director of the Center for Digital Trust, to introduce our guest. Enjoy the evening. Thank you.
Good evening. Welcome, dear friends, dear colleagues, to this lecture. So it's legitimate, it's a genuine pleasure, actually, and privilege to welcome an alumnus. Marc and I met, I think, roughly 20 years ago, when he was still a student here at EPFL, because he bravely came here to EPFL to do the whole thing, right? So bachelor, master, PhD. His PhD he did, actually, as he might tell you, he even took and even remembers some of the classes I was delivering at the time, and did his PhD with my close colleague, Jean-Yves Le Boudec. And so we were actually quite close to each other geographically. And then he moved on to a very long internship to IBM, 20 years, right? And he's going to tell us about his achievement there on something that, as Leïla mentioned, is immensely timely, and which is, once again, the, let's say, sometimes non-desired consequences of technological evolution, that one progress on one side actually leads to a challenge on the other side. And as mankind, we know, is very inventive when we are used to this kind of situation. So without further ado, Marc, thanks a lot for coming all the way from Zurich and for telling us about this wonderful topic. Thank you.
All right, thank you. Thank you, Jean-Pierre, for this very nice introduction. Thank you, everyone, for joining here. I'm really pleased and honored to have this conversation and discussion with you tonight on, like you said, a very important topic, one topic that will touch all of us. You may not realize it, but we are going to be exposed to this, and we're also going to face some of the interesting challenges, you know, as it is progressing. Now, it's really nice to be here at EPFL. It's a place where I really benefited a lot from super high quality classes, but one that I wanted to specifically highlight was the class of Jean-Pierre Hubaux, where I learned something that created a very special memory in my mind, which is at the very last class, last lesson, he went to the board and he drew a diode, diode en français. And he said, look, this is research, and on the other side, this is industry or economy. And once you pass from left to right, there's no way back. And this stuck to me because I said, I want to stay on the left as long as you can, because very quickly one gets sucked into the right, and it's really hard to get back. So I'm still trying very hard to be staying on the left, and I'll show you a few of the examples of what we do and how we work in IBM, in research, and some of the impact we can have being in research. Now, just a few words about myself, or about the structure or the team I'm running. I lead the security research department in our lab in Ojjeh near Zurich. About 50 persons, very much focusing on topics like cryptography, also applied cryptography, and you will see some examples of what we do and how we trying to be very successful in this space. But we're also working on many other topics, and I see some familiar faces, collaborations we have here at EPFL, for example, with Matthias in different areas. All of it really focusing on this idea of how do we improve security from an industry point of view? How can we raise the posture and make things harder? And every time I speak to my team, to people I work very closely with, it's the typical question that I show this chart for quite a while, but I think it still sticks. Security is an arms race, right? Good and bad, constantly, I'm playing this cat and mouse game, a new technology being introduced, this technology being misused or used by attackers to do something, and then there's a counterpart. We have to fix this, and we've seen this in all eras of computing, in the PC era, in the web era, in the mobile and cloud era, where new threat vectors came up, and we had to fix and close these threat vectors because they were exploited very quickly. And this is not different for what we call the next era of computing, and the next era of computing can be many things. There are two examples of how we look at the next era of computing. So if you look at classical systems that we have today, we're very familiar already with AI systems. All of you have probably used ChatGPT or any other large language models and chatbots. And now there is also a new type of computing becoming more and more practical, which is called quantum computing. Quantum computing using qubits as a unit, as we call it. And quantum really, I think, is very special because in computing, if you think about the history, the last decade, basically, we've seen a progression in terms of computing power that was, in a way, predictable and followed a certain theorem. And now, all of a sudden, quantum is the first time where we see that this theory may not hold, but it actually branches significantly. So instead of having bits and to kind of double the performance of a computer or the power of a computer, we had to double the number of transistors. Now with qubits, you can basically double the power of the computer, by basically just adding one more qubit. That's the theory. Remains to be fully proven, but that's where things are heading. And that enables a number of new applications that, for those of you who are not so familiar with quantum, just quickly wanted to illustrate with one example, which is about this example of representing the energy configuration of a single caffeine molecule. On a classical computer, you would take 10 to the power of 48 bits. So that's about roughly 1% of all the atoms on the Earth. On a quantum computer, you're only representing or need 160 logical qubits because there is different ways of how this information can be encoded very specially on a quantum computer. And in this way, using these qubits, you can do calculations that are much more powerful, and you can solve problems that you couldn't solve before. I stay fairly abstract for those of you who are much more deeper in the topic, but for the sake of interest, we can really think, if you think about the space of all possible computing problems that exist, there are some of them that are easy, that we can already solve today with classical computing, and there are hard problems that cannot be solved. I'll give you just an example later on. Now, quantum computers enable us with a new set of problems that we could not solve before. For example, there are ways you can do new simulations, you can find new materials, you can do optimizations that would have been algorithmically, from a complexity point of view, far too hard. There are also ways you can simulate quantum mechanic effects that on a classical computer you couldn't do before, or was not even part of a computing problem. But there are other problems such as factorization of large numbers and discrete logarithms, calculations where quantum computers are fairly powerful in. And since I'm at EPFL, since I'm at the kind of technical school, I'm going to do a bit of math with all of you and see who is fit and ready. Keep it still fairly simple first. So this is what we probably all know, multiplication of two numbers, very simple to do. Now, if we take the other way around, factorization, I mentioned before. Who's the first who can give me the result? Yes, 7 and 13, correct. Still pretty simple, we can do it, but we already realize it's not so easy to do this, to find the 2 prime factors. Now, if I go to the next level, 2 300-digit numbers. Humans, of course, not easy. However, our computers today, even a credit card, as simple as a device, very quick. Less than a second to do this multiplication. The other way around, factorizing a 600-digit number, even the most powerful computer today will take millions of years. So this shows, an example why factorization is a hard problem to classical computers. There's no efficient algorithm to factorize or to find the prime factors. Yet we see challenges, or this is actually the reason why we have cryptography, because cryptography is using mathematical problems that are hard to use or hard to solve, and in another way they're easy to solve. So for example, someone who is invited in a conversation has to basically solve the upper problem, an easy problem, but people who are not invited in a conversation would have to factorize the large number into the prime factors to be joining this conversation and read the message. So a lot of the cryptography that we see today being used to secure our day-to-day conversations, to create digital signatures so that we can trust that we're really talking to the right server on the other side, or that a document is properly signed, or we can trust an update we get on our phone, is secured using what we call asymmetric cryptography that relies on exactly such hard mathematical problems. You may be familiar with terms like public key encryption, digital signatures, or key exchange algorithms, which help us that we don't have to first walk to a server, exchange a key, and then I can securely communicate, but there are protocols and ways how you can interact with the server to establish a secure communication without having met before. And there are some very famous algorithms like RSA, DSA, elliptic curve cryptography that are exactly relying on these principles. Now, like I said, there's going to be a bit of a challenge because some of these problems that the cryptography community has relied on for many, many years is going to be put in question because there is an algorithm that is already known since the 90s called Shor's algorithm. Peter Shor, a mathematician, has figured out that with a smart enough algorithm on quantum, you can solve these problems within hours. And that puts basically in question a lot of the cryptography that we use, that our digital ecosystem relies on. Actually, our entire e-business that we use, e-banking, everything is entirely built around the security. We're only using e-banking because we have security, and of course many more things, and that's going to be put in question. Now, really, what can a cyber criminal or someone with a strong enough quantum computer do? It's very simple, actually. Basically, if you look at the main 3 principles of cybersecurity, confidentiality, integrity, and authenticity, is all going to be affected. So someone who has a quantum computer can decrypt communication. They can basically manipulate interactions to a system, so affect the integrity. Or if they have a digital contract that has been digitally signed, you can change the contract and re-sign it, and there is no way to distinguish which was the original contract and the contents of the fraudulently modified, forged contract. So you can see it's actually touching pretty much everything. And that shows the breadth of the problem. But we also have a different problem in addition here, which is that it's not only a problem after when these cryptographically relevant quantum computers are available, but also already of today, that data that has been encrypted today can be decrypted in the future. So think of the reality that you're having a conversation with someone, you think you're secure, but in a few years, and I'll talk about some of the timelines, this can be decrypted and can be seen, and that's a problem that creates also some level of urgency to this entire situation. Now, what's really at stake? the challenge really is cryptography is everywhere. It's in all the internet protocols we know. It's used in all kind of digital signatures. Critical infrastructure is heavily relying on cryptography. But then also our entire financial systems, all these protocols there are using cryptography. Blockchain, even cryptocurrencies, to some extent use cryptography. And of course, the entire enterprise and security. Also our private life with all the updates we get on our phones. Or, I'm not sure if you thought about it, our Swiss passport or any passport is using a digital signature in the electronic part, which at some point can be addressed. And that's really the challenge that we have. All of these things have to change. They have to change over the next few years, but they have very long update cycles. So passports live for 10 years, some vehicles on the road up to 20 years, and even more systems have a much longer lifetime. So you're not just easily replacing these things by rolling out new systems. And on top of this, the data that we use is regulated. In many industries, have regulations to stay secure for 5 years, 6 years, 10 years, 20 years, depending on the industry and the type of data. So what it means that is that if you encrypt something today and you put it in a backup and you think this is secure, I don't need to care about it, at some point, some organizations have to rethink, is this really still considered to be secure? Because now we're in a quantum era and it may not be secure anymore. And that shows a bit the extent of the problem that we're facing. Now, this can be a very, seen as a very bad news, and I think it is, to some extent, the challenge that we have to face, but I wanted to really focus on the good news. The good news is that quantum safe cryptography that is safe, already exists. We see also a lot of awareness nowadays with many organizations, with governments. We also see advisories and guidance being provided by government institutions, and there's movement going on finally. I say finally because we still have a big journey in front of ourselves. But just to quickly give you a bit of a summary of this quantum safe cryptography. In 2016, the US National Institute of Standards and Technology has launched a competition called the PQC competition to standardize new cryptography that is safe for the quantum era. There were over 70 submissions of different algorithms from all around the world. And we've also submitted some of them, not me personally, but have some really clever, strong cryptographers that worked together with other institutions. And we were in a very, very lucky position where that all four that NIST has selected for standardization to become basically the future of security, of asymmetric cryptography, we were participating in. And what you can see here are 4 algorithms. One of them is a key exchange algorithm, so this is what you can think of encryption, and 3 of them are digital signatures. And now last summer, they have been standardized, so they have first been selected, then the standards have been written and released, so they're actually usable nowadays. And that's really where the challenge is going to be, because using cryptography and changing cryptography is not so easy, as we will find out. So if you think about this timeline, we had 2016 and 2024 when the standards have been released. We knew about the problem since 1994, so one could say not much has happened or had to happen, but now we have some predictions when it may be possible that RSA 2048-bit encryption could be broken, and there's different reports. I use here the NIST report. They say it is likely to happen, or it is a good chance to happen by 2030. And then in the US specifically, but also in other countries, there are increasingly more government guidance that we should disallow old classical cryptography. In the US, for example, it's 2035. So what it really ends up with is that we had 36 years to prepare, we had 8 years to find the standards, and now we have only about 6 years to really accelerate and migrate. And when I say we, this is not you and me necessarily, because we're using systems, we're using devices, we get updates from somewhere, and we may use an online banking system of our bank, or we may use some other tools, and someone has to do the work for us. We can probably, as individuals, can be a happy user to do so. And good news for you, if you're using Android or you're using an iPhone, Apple or Google have already started putting this. So if you use the Chrome browser, it's already integrated. So they're already using MLChem, and in the future they will start to enforce it even more, but today it's already the default. If you use an iPhone, they're also using MLChem for iMessages, for example. They've implemented it there, and more is to come. So as an end user, for us, this is going to be solved. But the big challenge is going to be the enterprises that have lots of software, lots of dependencies, and I'll briefly talk about this next. So what we see is really that all around the world, in the US, there are timelines. In the financial sector, the Monetary Authority of Singapore has issued some guidance. In Europe, we have all member states, security agencies who have put a strong emphasis, and even in Switzerland, we have some first interpellations and guidance there to do so. But I think the most concrete one, I think the one that just recently came out from the UK National Cybersecurity Centre, is very simple and straight. Start now to get full awareness, then define your goal, and by 2031, so they diverge a bit from the 2030, really focus on all your critical systems, and then full migration by 35. So they say, this is the UK guidelines. Israel is much more aggressive. Australia is also very clear. By 2030, all the cryptography has to be banned. So every country is doing a bit by themselves. And the challenge is now, how do you execute this? How do you make this viable, cost efficient? Because at the end of the day, the challenge is there is no return on invest. For an organization to change cryptography, you're not going to make more money. So why should you do it? First problem that we often face is that they are not even aware. So no awareness of the situation, of their posture. Standards are still somewhat changing. It's not an immediate threat. We talk to quite a number of security professionals. They say, oh, this is a problem of my successor. It's 2030. I don't need to do anything now. I have bigger problems, and I'm going to be hanged for maybe phishing or any other near-term threats. So it's a problem of the future. And how do I create and close these visibility gaps that most organizations have? Like I said, cryptography is everywhere. I took an example here, a laptop like this. We ran a scan. We found 200 instances of cryptography on a single laptop, because every application packages something in, they use something, and it's very hard and difficult to manage this. And most of these systems are not even what we call crypto-agile, so it's not easy to replace, because cryptography is somewhere done by a developer, put something there, yes, I follow the best practices. It's not easy to replace this in many systems, especially when you talk about embedded devices, for example, or if you have even a hard-coded master root key in a device that you cannot change, because that is by design it's there. Plus, there are lots of dependencies and not very many skills in the area. That's a bit the challenge we deal with, and also where my team and an extended team in IBM and in many other organizations, by the way, as well, are now really very heavily focusing on how can we make this transition, this transformation doable. And to give you a bit of insights at the high level of what are the challenges, it's that if you look at an enterprise and a complex IT environment, they have software, they have software as a service, they use network equipment, they have data that they encrypt, they have contracts, they have any device you can imagine, and these are things that they're using. So that means they have to change this. But what they actually not have is control over it, because they use this from a supplier, from a vendor. Maybe for some organizations they do a bit of implementation, but in our experience, 90-95% of the software that someone is using is third-party software, or it's a platform that they build on top. They use Kubernetes, or they use OpenShift, or they use libraries that come from open source, and they depend on what the software supplier basically put in there. So who can actually make some changes is the lower level here. But even there we realize if I buy a product, say I buy a product from SAP or I buy a product from Microsoft. Microsoft is also reusing someone else's code, so they also depend on another third-party supplier or an open source project. So it's a long, long chain of dependencies. And if you really break it down into looking at this at an enterprise, the challenge that we're facing is that there is no cryptographic inventory. It just doesn't exist. People have not cared about it, so they don't know what cryptography they have. And they really need to break this down into all the dependencies and risks and where does data actually flow so that they can at least work in a more or less prioritized manner. So it's what we call an optimized change management. So we have to think of what are some of the urgent actions, what do I really care in a few years, and what can I maybe do with other projects where I modernize my IT anyway, or I do a network upgrade in 3 years so I can align it with that and work with my suppliers. So this is one angle of how do we do this optimally, how do we help them planning, how do we help them discover some of their risks and come up with solution patterns and architectural design or decisions that will help them to not waste a lot of money. On the other side, you may say that, hey, we have this software, let's just scan it. Let's just look for cryptography in our environment. Now, the problem is that most organizations don't have access to much of the software. And like I described before, cryptography may be hidden somewhere in a framework I'm using, in a web server, maybe in a runtime platform, and very rarely it is visible in the source code itself. So the challenge that we're facing here is how do we exchange information about cryptography? And here we have recently published a new standard that we call cryptographic bill of material. It's basically helping us to document cryptography and exchange information about cryptography and software. For those of you who are familiar with software bill of materials have become very prominent when there were some incidents of third-party open source that you couldn't really figure out do I have this library included in my software? So it helped to understand what is actually in a piece of software. We have taken the same standard, we have extended it and added cryptography and now work very closely with the Linux Foundation and OWASP to create or to promote this even more so that people use it. And we've seen now already governments who have issued very concrete guidance to use these cryptographic bill of materials as a basis to exchange information about the cryptography organizations are using and report on their progress to migrate to quantum-safe cryptography. And at the same time, we're working very closely, and this is a very dense chart on different methods, technologies, strategies to support and advancing the discovery, the awareness, the prioritization, the decomposition, all the way to the remediation of cryptography, both at the enterprise level on the upper side, but also within individual software and apps so that they can become or get to a better state. So very concretely, one thing we have done is that we've implemented a piece of software that is a proxy, a network proxy, that can lift communication into a quantum-safe channel. So for example, if you have an online bank where you have an access to the banking system and your provider does not allow you or does not yet provide quantum-safe cryptography in the web service, you can lift the communication into a quantum-safe encrypted channel in addition to the regular encryption, and your client, so for example the mobile banking app or the browser, depending on its capabilities, then will get the right level of encryption. So you can measure where you stand, where your clients are standing, because you depend of course also on your clients. Have they upgraded their phones, or are they still working on an outdated version of the browser? So you can measure where you stand and move them into a quantum safe state over time. And with that, I approach the end. So what we really communicate a lot at the moment, it's not new, it's already for a while, but we have been saying you need to start preparing now, and it will be now for quite a few years to come. But what we really see at the moment is that the awareness is raising significantly. It is becoming a boardroom topic, so all the way to CEOs and to chief risk managers. They realize the need that they need to act. They don't need to act on everything. They need to act on the things that matter, and then start preparing for this migration and aligning this in a way so that we can orchestrate this in a clever manner. And with this, I end and would like to leave this as a takeaway from you and for you, and I hope that you found this interesting and useful as a topic that we're working on.
Thank you so much, Marc. Please have a seat. So we'll now move to the question session. So let me maybe start with one question, which is, and then we'll open to the floor. But one question I would like to raise is the synchronization issue, right? Because as you pointed out, just for one single organization is very complicated because they don't know, right? They don't have a kind of repository or a kind of file where they would have the list of cryptographic algorithms used and where in which part of the software. So they have to do this, right? They have to find out and so on. But crypto is used especially in order to communicate with other organizations, right? And so they have to synchronize switching from one, let's say, weakened let's say, algorithm to the new ones. It could be lattice-based, for example, that would be actually quantum proof, or supposed to be quantum proof, hopefully. So can you say something about how this is going to happen? Because it has to be worldwide, right? So it has to also be at the international level. I presume you have to install the various versions, and then at some point the protocols are going to switch, right? But that's easy to say. In practice, I guess it's going to be more complicated. Maybe you want to elaborate on that. Yeah, no, it's a very good point. I think in some scenarios it's not so difficult. In others, it's terribly difficult as usually.
So for when we talk about communications between two endpoints, it is luckily we have some support of protocols. So TLS, as one example, there is a negotiation happening. Both parties disclose their capabilities, and then they determine what is the best or strongest kind of capability. And once there is a quantum safe cipher and both of them support the same, then they will agree on it, and then they will use this one. And that's what already is happening. If you go, for example, if you go to google.com and you click on that little lock icon, then you can look at what is the type of encryption and what is the type of signatures I get. If you have a recent phone since or browser version since May this year, you should get MLChem, and you will see it there already. So in long story short, for this example, both parties can basically update independently. They have to, though, adhere to the standard, which luckily there is a standard now, so they know what to aim for, and then this will happen. It'll become more complicated for some protocols, and especially for public key infrastructure and certificates, because there it's a top-down, and if you switch your public key infrastructure and you get the certificate. By the way, there's not yet even a standard of how to do hybrid certificates nowadays, where you have maybe classical and quantum safe ciphers. So this is still in the standardization. But there, at some point, you have to make a decision, especially because some of the devices may not be able to support these certificates, and they may even say things are too large or not powerful enough to do it.
Okay, thanks a lot. Can you say something, please, about satellites?
Satellites. It's another interesting topic, but I don't have much insight into that.
You see the point, right? Because satellites are extremely difficult to retrofit in some cases. Well, because they're up there, supposed to bring them down to. And so if something is vulnerable, and we know how sensitive actually satellites are, especially nowadays, how is it going to happen, right? Also because satellites sometimes operate in a multicast fashion, and so the challenge might be also delicate in this case. Yeah.
Well, I can make some speculation. Of course, satellites have ways to get updates injected. Now, there are a number of complications we should be aware of. An update, similar to our phone or to our laptops, they're typically signed so that no one can inject the wrong satellite. So how do you update the key that it's verifying that it's a legitimate update, without compromising the system? Now, the good news is there's still some time, right? I talked about the dates. It's not today, right, where the threat is happening. So if you do it early, you can update to maybe a hybrid key, and then you can preserve this. But the second challenge is going to be that the hardware may have to support other type of optimizations than how it was optimized originally for. The good news is the new algorithms, the MLChem, MLDSA that I mentioned before, they are what we call drop-in replacements. So drop-in replacements mean we can basically exchange them. They come. You don't need a quantum computer, for example, right? You don't need a new architecture. You don't have vastly different criteria or changing, parameters in the calculations. But there are certainly changes overall in key sizes or in the performance to compute or verify a signature. And some of them are even probabilistic in nature, which means that there are also other worst case scenarios to be considered. So that makes it more difficult to make this migration. You have to test a lot. It's not just replacing. But if you think about credit cards or passports or other things, these algorithms still work on these embedded devices without having new characteristics or need for new characteristics at large.
Okay, thanks. There is a horror scenario, right? That if things are upgraded too late, the upgrade itself is going to rely on the existing crypto systems, right? And if some quantum system is able to break that, then it means that it can actually inject stuff that is going then to be present in the new infrastructure without actually the people doing the upgrade being aware of this. Right, and then the whole system breaks apart. Right?
Yes, and I think I can give maybe an illustration of such an example. It's a slightly different one, but if you think about a digital signature on a contract, we always talk about harvest now, decrypt later. There's this problem of if you harvest some encrypted data, you can decrypt it. This is a problem of today. Digital signatures will only become relevant or once the quantum system exists. So everything that is digitally signed today, is still secure until there's an expectation that this quantum computer exists. So what you can do today for the next few years, you can still sign it with a quantum safe signature. And then you have basically a proof with the date that this has been done before a quantum computer credibly existed, and you have basically, that chain established that you can do it. But your problem is exactly the opposite. So if you don't have it, if you're too late, if that system there is a chance that someone may have compromised some master key, and the update is not trustworthy anymore necessarily.
Okay, thanks, Marc.
I think I want to say, I think we should. There are so these are extreme cases from time to time. I think it's always interesting also to think of what are the initial risks, what are the initial targets of someone who has a quantum computer in their basement. We're not going to read about it in the newspaper. I don't expect that, but maybe some very high valuable key is all of a sudden compromised. And see a few security researchers in here. I'm happy to listen to opinions. What is going to be attacked first, or what's the most valuable target?
Okay, thanks. So maybe we can open the questions from the audience. So if you have questions or suggestions of high-value keys to be attacked, you may want to actually walk to one of the two mics. One is here, and the other one is over there. And please don't be shy. So please, yes, please.
So first of all, thank you very, very much. Very, very interesting. Are you doing research on what the collapse of current cryptography will look like? It is not like one day in 2030 that everything will immediately collapse, but it might be possible to breach some system at a very high cost, very, very slowly, with some reliability or some probability, and it will be a process before it becomes very easy to break any key of any time in the past, and probably that reconfiguration may last 5 or 10 or even more years. Do you have some ideas about that? And if you have a slow or gradual collapse, then perhaps the strategy may be easier to implement than if you have a sudden one.
Yes, very good point, very on point, right? Because at the end of the day, the question is, what are the most high-value targets on the one side? So this is what organizations think about. On the other side, if you think about from a society or from a government, like say, take the Swiss financial system, or take say some military organization, you have to think really holistically. So we're actually looking into some of these scenarios, and you'll find very interesting settings, that some things that I wouldn't have anticipated a few years ago. Many organizations use, for example, trusted information, trusted time, for example, for trading. Which, again, what is trusted time? It comes with trust, comes with cryptography, or say currency exchange service. Again, you rely on this, you may not think of it first, and then you start to model kind of some of these threats and how it evolves. So in many ways, yeah, we're looking at these scenarios. We do this with organizations. We also do this with various national cybersecurity agencies, and advise them basically on where to look first, and where's the highest chances for their ecosystem, for their sector to be exposed. Yeah. Thank you.
Okay, Matthias, please. Yeah.
Thank you very much for the super interesting talk. I really appreciated the how you abstained from fear mongering and everything is going to break down and burn down. Great work on that. You mentioned that like we're going to reach a point where someone will have a quantum computer in their basement, and I would like you to distinguish a bit in the threat modeling between someone, as in a quantum computer exists, and anyone.
Yes.
Because there's a huge difference between a nation state, and a nation state is likely not going to be interested in stealing the little bit of money I have in my account. But anyone that as soon as this can be used by organized cybercrime, it's going to look very, very different. And maybe you want to distinguish between the threat models and also the timeline a bit on the exponential cost in these kind of systems.
Spot on. I fully agree with that. So the very first cases will be very difficult to identify, and maybe we will never actually be able to tell which one was the first actual factorization. There are many players around, right? Lots of investment in the technology. Some of them is visible, some of them is not. But then, it gets more and more commoditized, but not commoditized, I guess, in terms of that everyone has access to it, but maybe some organized crime finds a way via indirection, so after nation states. But I think even at the nation state level, scenarios we've looked into is, how can you destabilize an entire country, or can we destabilize? Again, I bring the example of the Swiss financial sector by just, blackmailing all the banks that their certificates are basically exposed or their systems are down. So there are various scenarios that are possible. I don't want to play doomsday here, but I think the thing is to create the awareness, because now we still have time, and many things are being upgraded. So organizations today that plan ahead, that put it into their, say, when they procure a new system, they procure a new piece of software, they can already plan ahead and speak to their suppliers that, make sure it's going to be quantum safe in 3, 4, 5 years. Not that when they roll out a new system, then they realize, now I have to redo all of this again because, I haven't thought about quantum safety. So this is why we come early, because we can limit the damage and we can save a lot of money. Yes, yes, I would love to, yes. Yeah.
What's the trade-off?
Trade-off in terms of what?
Use the mic, please, yes.
Like the question I asked, do we need a crypto bounty system orthogonal to a bug bounty system? And the point could be made that bug bounty systems are so much just a cheap way for companies to kind of delay their search for bugs and vulnerabilities and outsource it to third parties. While they're important in some cases, there's clear economical trade-offs. And it's kind of like maybe after we've done the majority of the migration and have a reasonable understanding of the cryptographic primitives that are being used in a given system, we may want to extend and use this as an orthogonal measure. But how do you balance these different incentives and make sure that this actually works in practice?
Yeah, I love the idea because I think there is actual value to, I mean, I guess like I described, the first few changes are going to be very prioritized and driven by objectives. But at some point you're saying, okay, look, let me switch all of it over. And of course, to get the very last one to change, which I'm realistic enough, it will never happen, right? We still have very old cryptography like triple DES and other things in use today. Heartbeat is another one. Yes, exactly, is a good example. It's still, these vulnerabilities exist. But I think it's really about what matters and what doesn't matter. And I think a bounty like this could help. I would like to probably chat offline with you of ideas of how this could be instantiated and lifted off. Yeah. Yeah.
Good. More questions?
Yes.
Yes, please.
There are currently 3 signature algorithms that are standardized, if I'm not mistaken, based on 3 different primitives. But there's only one key encapsulation algorithm. Is there more in the works? Because they are still pretty new on a grand scheme of things of cryptography, and we assume they are post-quantum secure, but it's not really tested as long as, for example, RSA and so on. What is the plan in that regard?
Yes, absolutely, good point. So first of all, yes, there is another NIST competition going on for digital signatures specifically. It's called the NIST on-ramp. The reason is that today, the 3 that have been selected are all related to lattices. And they want more diversification of the underlying cryptographic primitives. Exactly for that reason, let's say if for whatever reason it may turn out or not, we're pretty sure it will not, but that there's a flaw, right? Right now there is a new call, or that the call happened, so there are multiple rounds again to find candidates. And we're also participating. We're part of 4 of new submissions. They all have very funny names: Unbalanced Oil and Vinegar, and Mayo, and other things. In a couple of 2 years or so, we expect that we have the findings for NIST as well. Also, on the point of key encapsulation, there is another one that has been selected actually, and is also on the path for standardization to also add more diversification. But I think that gives me a good, clue, or basically also talking point about agility, because what we're expecting is that cryptography will not be used in the future similarly how it has been used today, that is somewhere, in the back of, of a piece of software, very hard and to understand and embed it. But where we see now a lot of benefit is to use this transition for organizations to become what we call crypto-agile. So how can we use cryptography more, as a service or configurable, as opposed to be, hard-coded and embedded as it is today? And there is ongoing work on how do we extract cryptography, externalize cryptography out of an application, more that it can be better governed and better controlled and upgraded, so that it's easier to be changed if there is change needed. Like I said, I don't expect so. Work very closely with our foundational crypto team and also look into the challenges, but you never know. Cryptography believe it or not, can only be proven to be insecure. You cannot prove it to be secure. That's the reality of cryptography.
Please.
On that note of proven to be secure, when you say quantum safe cryptography, I assume what you mean is a classical cryptography method or algorithm that is safe to current quantum day algorithms like Shor's. Why, if this is the case, do you not want to move for actually quantum secure communication using quantum channels like maximally mixed states that are not just secure to current day quantum algorithms, but secure to all quantum attacks because of maximally mixed states, for example?
Great point. So there are things like quantum key distribution, QKD, and others that use exactly quantum effects where you have the physics, really giving you the security assurance. And it's a great technology. Actually, I can brag a bit. It was invented by IBM in '84. But we are actually not putting this as our main solution just because, well, there are a number of solutions. One of them is practicality. You would have to have a line that you can rely on. If you have a credit card or phones, it's very difficult to implement it. It's only looking at confidentiality, so it's not really looking at integrity because they're still falling back on MLDSA for integrity and authentication. And there's another challenge that I think is often overlooked. The idea of QKD is that if you can tamper, if you see the channel has been tampered with, then someone has broken the challenge. So it's perfectly secure from that point of view, but it's also perfectly disruptible because you just disrupt it once and you disable the entire system. So there are a number of trade-offs. I think there are some really good applications. I know some central banks are experimenting with key agreement, key exchange. But I think for the large-scale use, we have to rely on the mathematically founded cryptography, so the post-quantum cryptography, or we call this quantum safe, but I think this could be a bit of a misnomer.
If I can add to that, so let's say we have distributed quantum computers in people's basements or phones through cloud computing, and some genius comes up with a new, better Shor's. This could potentially break all your quantum safe cryptography overnight, and this could expose everything that you sold to people as quantum safe. Do you not worry about that?
Not so much. Of course, it can happen, but it could have happened with RSA or DSA as well, that from one to the next day, someone found this groundbreaking algorithm to factorize large numbers. The cryptographic primitives called lattice-based cryptography, which I skipped in the interest of everyone, is exactly in this other space. If you remember the Venn diagram where you had the hard spaces and the easy spaces and now the quantum possible spaces, these problems, these mathematical problems, this is how this cryptography was basically formed. There was a lot of research to figure out what is going to be not, exponentially easier solvable with a quantum computer as opposed to, the problems that are going to be. So there is good confidence, there is no guarantee.
Okay, thank you.
Okay, we have time for one more question. Yeah, please.
I just had a lower level question. What is the complexity of these quantum algorithms? You mentioned space, which has embedded systems, which could struggle with this sort of thing, but also people in lower, how would I say, more difficult situations than in Switzerland, where computing power is also lower and stuff like this, and how do these standards kind of interact with that?
Yeah. I'm happy to point you at some of the papers we have done. What's really interesting, they are at the same level computationally, some of them, so there are different trade-offs that are at the same level as the classical cryptography, but then they come with a trade-off that they may have a bit larger key size, so you have more network bandwidth you're using, or the signature size is larger. So we have done a very solid analysis. Actually, just 2 weeks ago, we've been at the SSL conference, I think it was, where we've just published a very interesting study on how this impact happens at the server side, where you have a lot of concentration, and since you have some non-deterministic execution, you have very difficult, queue sizes to manage. But what we noticed, and especially with the new signature algorithms that are currently being standardized, they are very comparable. They are always comparable, but they're on par with the existing algorithms, and some of them are even faster.
Thank you very much.
Welcome.
Okay, we still have time for one. Okay, very good. One very last question, and then we'll wrap up. Please.
Thank you. Good evening, and thank you for the presentation. I would like to go back to your introduction because you said, with the diode, and you draw the line between research and the business side of things. You work for an American company here in Europe. According to some sources, Europe leads the way in quantum technologies and in the field of research. Would you say that Europe has the resources to pass this line and go to the business side, and to have some companies that compete with US and Chinese companies?
I hope so. Absolutely. I mean, we have the skills. I think there's no question. I think if I look at all the 4 algorithms that NIST in the US has selected, they were all out of Europe, driven out of Europe, with skills out of Europe, but very few partners in the US and other countries, but they're European. I think this gives us a lot of confidence that we have the skills. I think the question is more, can we pick up the steam? Do we have the right models to create and incubate businesses? I have no doubt that we're capable. It's a question of, but you probably answered the question, are the resources there? I'm not sure. Jean-Pierre, you also wanted to add something to this.
Sure.
I'm confident that we could.
Yeah, but it's a very old, actually, question to know, how is it that Europe is, as mentioned, as you said, pretty good or even extremely good at the more academic considerations and doing stuff that is intellectually brilliant, but that doesn't bring much money, right? As opposed to the ability, let's say, to the US ability to develop systems that then go to the market and then are sold domestically and then are sold to Europe and worldwide. This has been analyzed, by many people, and this goes maybe somewhat beyond the discussion we are having here, but the short answer is that essentially it's really to the size of the market, of the US market, that is very homogeneous, the willingness, the entrepreneurship, the availability of capital, and other things. There's a report by Monti, Draghi, sorry, by Mario Draghi, who, at the request of the EU, has produced actually this report that explains that actually Europe tends to currently fall behind on a certain number of topics. And so there is certainly awareness of the issue, but this is something that is not easy actually to fix. And as you know, even the creation of the European Union in 1957 was an attempt to reach a size of the market that would be more amenable to have success stories to the extent we are talking about. And 68 years after, we see the European Union is still partially integrated, and actually there are plenty of tensions within the bloc for a number of reasons. But thanks for raising this up. This maybe makes it possible to finish on a more global note. So Marc, thank you very much again, and we'll invite everyone to the aperitif here next door. Thank you very much.